Hi guys, today we're going to talk about a very popular problem called the Monty Hall problem, which is often used as a classical example of conditional probability. Conditional probability is calculating the probability of an event provided that some other event has happened or is going to happen, right? And Monty Hall problem has been named after this game show host called Monty Hall. Not this person. This is some random guy I found on Google, but Monty Hall was a game show host. He used to host this show called Let's Make a Deal. He may or may not have been behind this thing, but he was a creative game show host nonetheless. He used to come up with creative ideas all the time, or that's what I've read, right? And the reason why I decided to make this video in this particular way is there are many simulations on the Monty Hall problem across the web, and I could have also gone on with making this simulation by using decision trees, but I later realized that it's better if we try to visualize this problem in this particular way, and that's why I made this little arrangement for you guys, right? I'll let you guys be the judge whether it's useful this way or not. Okay, so let me get started with the simulation. Okay, so before we get started with the simulation, I have done something, which is I've ordered these three doors in this. I've numbered these three doors, right? But I'd like to clear out that the order here does not have any bearing whatsoever. The order here does not matter, but for the convenience of the simulation, so that we can see how things unfold, I have numbered these doors, right? And the main idea behind this game show is that behind one of these three doors there is a brand new car, and behind the other two doors there is nothing. There are quotes, right? Basically you win nothing, right? So your objective is you have to make decisions based on maths, based on statistics, based on your understanding of conditional probability in a way that maximizes your chances of winning the car, right? And the game show host here will try to make sure that you don't win anything, right? Otherwise what would have been the point, right? And before we get on with the simulation, I'd also like to point out two things, right, which is very important and which is very crucial to this simulation, right? The first point is that the three doors that you have in front of you are absolutely identical, which means that they do not have any particular feature that gives away what is behind that particular door, right? So the probability of the car being behind one of these doors initially is equal, right? So it's 100 divided by 3, which is 33.33%, or 1/3, right? And the second point is that it's very important to remember, and which actually has a lot of impact on how this game show is designed, is that the game show host here knows very well what is behind each of these doors, right? He's not in the same position as you the contestant, right? You as the contestant do not know what is behind each of these doors, but the game show host here very well knows what is behind each of these doors, right? So he's going to try to make sure that you don't win, right? So I've made, okay, just one last thing before we get on with the simulation is that I've done one more thing for your convenience, which is I have added this green down arrow so that we understand what door we have initially selected, right? For your convenience. Okay, so let's get started with the simulation. So as I've said, the three doors in front of you are absolutely identical. So the car, according to you, the car could have been in any of the three doors, right? So the probability of the car being behind door 1 is 1/3, right? It's 33.33%. And the car being behind door 2 is also equal, right? It's 1/3. And the car being behind door 3 is also 1/3, right? Okay, awesome. And initially you pick door 1. You could have picked door 2, you could have picked door 3, doesn't matter. We are going to go through all of the simulations to see what are the set of actions that you should take if you are thinking it in terms of conditional probability to increase your chances of winning the car, right? So you pick door 1, and then what happens is that the game show host then goes on to open door 3 and reveals that behind door 3 is a goat. And now the interesting part comes in. The game show host then offers you an option and poses a question whether you'd like to stick with door 1 or whether you would like to make a switch, right? Whether you'd like to stick with your initial choice, your initial decision, or whether you'd like to make a switch. And this is where the conditional probability comes in, right? This is where the conditional probability kicks in, right? You may think that you just have 2 doors left, right? So the car could be either behind one of these 2 doors, right? So the chances are 50%, but it's actually not, right? And this is where you really have to understand the concept of conditional probability. The influence of other events, in this particular case the reveal of what is behind door 3, actually influences the probability of what is behind the behind these doors, right? And for this particular situation, for the Monty Hall problem, you are better off making the switch every single time. So every single time we are going to make that switch in this particular situation. The moment the host reveals that behind one of these doors is a goat, we are going to make a switch, and as you can see, I have created this tally section, and we're going to keep a track of whether we win or lose if we make the switch, and see what happens if we make the switch every single time, right? So let's say we make the switch to door 2, and then the game show host decides to open door 1 and then opens door 2. And here, if you make that switch in this particular case, you win the car, right? So let me just go quickly update the tally. So in this particular case, if you had made the switch, you actually end up winning the car. Okay, so let's just start by picking door 2, right? Because when you start the game show, you don't know what is behind each of the doors, right? So let's start with door 2. You pick door 2, and then the host goes on to open door 3, and like what he did before in the previous simulation, he asks you the very same question, whether you would like to stick with door 2 or whether you would like to make a switch and move to door 1. Now you may think that the host here is trying to apply reverse psychology, and you're better off staying with your initial choice instead of making the switch. But it doesn't matter whether the car is behind door 2 or whether the car is behind door 1. You should be absolutely driven by your understanding of conditional probability, or of whether you're actually maximizing your chances of winning the car, right? So if you make this particular switch here, the game show then goes on to open door 1 and then open door 2, and you lose if you make this particular situation, right? If you make that switch, you lose. So let me just go on and update this tally here. You lose if you make the switch, right? Let me close the doors again and let me run the simulation one more time. This time we are going to start by picking door 3, right? Because you don't know, the car could have been can be inside any of the doors, right? So you pick door 3, and once again you pick door 3, the host goes on to open door 1 and reveals that behind door 1 is the goat, and then asks you whether you would like to stick with your initial decision or whether you would like to make the switch, right? And since you are only driven by your understanding of conditional probability, you make the switch, right? You are not trying to apply common sense here, right? You are not trying to see through whether the host is trying to apply reverse psychology or not. You should be absolutely driven by the understanding of probability and whether it increases your chances of winning or not. So you had initially picked door 3, and then when the host offers you the option of switching, you make that switch, right? You make that switch to door 2. The host then goes on to open door 3 and then also door 2, and you win, right? If you make that switch, you win. So basically 2/3 of the time you win if you make that switch, and if you make that switch, you lose 1/3 of the time. So basically you maximize your chance by switching every time, right? you may think like for example, when you were in this particular place and when door 2 and door 3 was closed, you may have thought that there's just two doors left and the car could be behind either of the two doors, and it's just 50% right, 50% chance of the car being behind each of the two doors. But it's actually incorrect, and this is where the concept of conditional probability comes in, right? The fact that the host has revealed has actually changed everything here, right? The event of the goat being behind door 1 has an influence over how the other events that is going to happen, right? And that's why Monty Hall is such an amazing problem. That's why we keep on seeing Monty Hall in films, in different examples, in different lectures, and there has been books written on the Monty Hall problem. And that's why I wanted to make this video and show you the visualization here. And let me just quickly open all of the doors and show you that it doesn't matter whether the car was initially behind door 2. The car could have been anywhere, right? And you would still be better off if you make that switch. If you make that switch, let me just quickly write it here so that you can remember. So if you make that switch, the probability of you winning is actually 2 by 3, right? It's 2/3. And the probability of you losing, if you make that switch, is 1/3, right? So it doesn't matter whether you're the only thing that you should be concerned about is you increasing your chances of winning, right? And that is the Monty Hall problem for you. And I hope this visualization of the simulation of the Monty Hall problem simulation helps you understand this concept better. And that's all for this video, guys. See you next time. Bye.